up, grade 11s? We're back. It is your time for maths. It is a Monday. I'm with a special guest. As you can see, it's I. How are you doing?
I'm all right, Lily. How are you?
I'm good, thank you.
Great.
Dina is also in the house joining us for the lesson. How are you, Dina?
Very well, thanks.
Okay, cool. So, Izai, tell us about your book. Izai wrote this awesome book, The Mathematical Genius in You. So, tell us about the book and what it's aimed to do and all of that stuff.
Yes. Good afternoon, everybody. I am Edzai Jobo, and I am a mathematician by profession. Yes, I wrote this book, The Mathematical Genius in You, which is a motivational book to teach you how to think like a mathematician, to teach you how to succeed in mathematics. As you know, maths makes the world go round.
Yes.
And after last week, actually, a lot of kids came up to me and said, "Are you the mathematical evangelist?" Yes, I am the mathematical evangelist.
Okay.
I'm here to spread the good word that everybody can do maths.
Okay.
You just have to work hard at it. You just have to be self-confident, right? And know that maths does not breathe. You are the human. You have dominion over this thing called mathematics.
Yes.
So today we've got a challenge where I think it's on Facebook.
Yes.
And everybody can answer. The first 3 people to answer correctly will get a copy of this book. So make sure you rush and answer this book and answer so that you can get a copy of this book. Thank
Okay,
you.
cool. Guys, don't forget the question will be posted on our Facebook page. The first 3 people to get it right and answer it get a copy of Izai's book, The Mathematical Genius in You. So make sure you answer. And guys, answer right underneath the post. Don't write on our wall. Answer underneath the post so that we can see all the entries. Okay, guys? Any last words, like to give advice to the grade 11s, grade 12s, grade 10s, our mindsetters at home?
Yeah, mindsetters, all I have to say is that grade 11, you are halfway through matric because your matric started in grade 10.
Okay.
So there's no time to relax. Practice maths. Maths can be conquered. You are the geniuses.
Yes,
Thank
guys, you heard it. Be confident. You are the genius, not the maths. The maths doesn't breathe. You have dominion over it. So with all that said, guys, we are going to take a very short break. Thank you so much, Izai, for all those nice words and for your great book. I hope the mindsetters will learn something from it. And those 3 lucky people, hope you guys are watching the Facebook page for that question. So let's take a very short break and we'll be back with all the regular stuff. Mindsetters, as you are joining us right now, we are doing maths with Dina. So Dina, what are we doing for the grade 11s today?
Thanks, Luni. We are taking you on another journey on the second part of our Euclidean Geometry section. So we're halfway through the Euclidean Geometry. We'll finish it off next week. So that's what we're doing.
Oh, okay, cool. Guys, you heard it. We're doing Euclidean Geometry. Such a fancy word. Don't forget to hit us up on Facebook. Our page is facebook.com/learnextra. You can catch us on Twitter @learnextra. Remember to download the show notes, the videos, the schedules, any other thing you want to know about Mindset Learn and all the products we offer on learnextra.co.za/live. Our lovely show is brought to you by Macmillan. So thank you to Macmillan for sponsoring our show. Don't forget to answer the challenge question that will be posted on our Facebook page. So with all that said, let's head straight back to Dina with the Euclidean Geometry.
Thanks, Luni. And I think that everybody knows that Euclidean is really the adjective that describes Euclid, Euclid being the Greek geometer that really kind of consolidated what people actually knew, but he kind of wrote it down, so it was kept through time. And we want to celebrate. We want to celebrate that people over the time, over a period of ages, have been able to record things that we can use today, and we can also support the future. And in terms of the future, it is Science Week this week, so we want to encourage all of you to just go to the Facebook page and answer that question and get involved, getting your brain acquainted with new topics, new problem-solving skills, and try and get one of those books. So let's celebrate Science Week and do as many activities as we can to really enjoy the magnificent subject that the sciences brings us. Right, without any further ado, let's get into the Euclidean geometry. Last week, we looked at the first 3 theorems. We looked at the angle at the center, the angle subtended by the diameter, and also angles in the same segment. And I want to take that a little bit further today. I want to do one task that will use the theorems that we did last week. And then I want to look today at what is a cyclic quad and look at the special properties that cyclic quadrilaterals have, and after that we'll end off with two riders involving all the theorems that we've done up to this point. Next week we will look at the tangents and the angles that are subtended by various chords and the way that they relate to a tangent, but for today we're only focusing on cyclic quads. So let's get straight to it and let's look at what the key concepts are that we have been dealing with over the last week. Okay, as I said last week, we looked at the angle at the center and we noticed that this relationship between the center angle and the circumference angle is, if this is x, then the angle at the center will always be double that. So that's the relationship between an angle at the center. Now we've got to be careful that we make sure that the chord or the arc that you've used subtend both angles. So if B had been placed elsewhere to subtend C, then that relationship doesn't exist. So the relationship exists because we're starting off with the same 2 points. Then we also looked at the angle in the semicircle is 90 because it's really an offshoot from these two radii. When these two radii become a straight line, it becomes a diameter. So it really is saying that this angle at the center is 180 degrees, which is obviously then getting that relationship of 90 degrees at the circumference. So the angle at the semicircle is actually related to the theorem. It's just the special case where the two radii become a straight line. Then the one which I refer to sometimes as the butterfly theorem is the one where if you take two positions A, B, and you then subtend at different places, we're then saying that these two angles are the same. And the reason we say that is because they're all related to some center angle. So if this was the center, then, and this is 2x, then because those chords subtend on the circumference, they will both be half of what that center angle is. And so I can draw an infinite number of chords to the circumference, and all the angles at the circumference will be the same size. Hence we speak about angles in the same segment, because this arc, we can draw a chord, and this chord separates us into the minor segment and into that segment. So all these pink angles are all in that same segment. Notice that all the points are in the circumference. Grade 11s, you've got to learn that all the theorems we will do refer to angles that have been subtended either at the center or at the circumference. They're never going to be in the space or in the area inside the circle. So it's very important to make sure that you are hooking your points from where you're subtending onto the circumference, and you're subtending either to the center or to the circumference. Then we get some offshoots of these theorems. What we call in Euclidean geometry corollaries are extended results from the particular given theorem. And the first one is that equal chords will subtend equal angles at the circumference and at the center. So over here, I showed you how the same chord subtends equal angles. So this chord's length hasn't changed. But if I take this blue length and I mark it elsewhere in the circle and I subtend from that chord, then the angles that have come off that equal chord, so it's an equal portion, they're congruent lengths, I can then say that they will subtend equal angles. So the chord doesn't have to be the same chord, but it can be of equal length. And in that case, that chord will subtend equal angles. Then we also get equal angles at circumference, which are subtended by equal chords. It's a similar thing to this. So if it's actually the converse of what we've just said. If you've been given this angle is equal to that angle, then if you take the chords from which that angle has been subtended, which is AB, and you talk about that length there, and you talk about the length DC, which is where E's come from, then my conclusion is that those two lines have to be equal. In other words, an angle is only subtended in a circle equal to another angle if the segments from which they've been subtended are the same. And then we can also talk about equal chords in equal circles. So you'd have to have congruent circles. This is very often not seen, but again, we're taking the idea that if you've got the same segment in congruent circles, then they would subtend equal angles. So That was really what we discussed last week. So let's just end off. This question was on last week's notes, but we didn't quite get to it. So I thought we would start with this question. Two circles, they intersect at A and B, and EAF and DAC are double chords. And it's always important to know why information is given. Why are they telling us that these lines are double chords? Well, if we look at it, it's EAF. It means that EA is a chord in this circle, and then AF continues to be a chord in the other circle. So what they're really saying is that these lines are straight lines. So we've really got that these are straight lines, because we noticed last week that the Euclidean geometry has been built over time, and we can utilize the results we've had previously. And if we don't know certain information, we're not going to be able to proceed. So we can't assume that lines are straight. We've got to be told that they're straight. So indirectly, they're telling us that. They give us the size of two angles, and then they say, please won't you find out what the size of DFB is. Now, it's useful to go to DFB and to say, okay, it's this angle I'm talking about, which is really angle F1 plus angle F2. So that we really know where on that picture we're on. Okay, so the first thing to do is to get familiar. Let's get familiar with this picture. We've been told that the EAF is a chord, CAD is a chord, so these are straight lines that are intersecting at A. The two circles also intersect at B. We've been given these two angles. Grade 11s, at the outset, when there's so many lines that are drawn, it's difficult to focus on anything, because those lines are just blurry. They're just all over the place. So the best thing is to always go to the point on the circumference and try and gauge what kind of information do I get from those angles at the circumference. So I'm going to take this first circle, and I'm going to go to point C and point E, and you must use your hands to help you, to guide you, to subtend. You cannot just stare at the piece of paper. You cannot just look at it and hope that it's going to jump out at you. It's not. You actually have to go and use your fingers, use your hands to move along to see how these angles are actually formed. So watch what I'm going to do. If I put my fingers on CE, that means I've got this minor arc, and I'm going to now follow from C and E so that I meet at a point. And can you see that I'm going to A1? Okay, so I can talk about angle A1. But if I go back to CE, I'm always looking for the same chords. I can also subtend at B1. Okay? And I spoke about that earlier, that it's these intersecting lines that create that butterfly theorem. Now, it is important to put your fingers on CE and to go and subtend at the circumference. I can't subtend here because that's not going to give me any relationship between angles. The angles that are related are the ones that are on the circumference. So firstly at A, and then secondly at B. So angle A1 is therefore going to be 31 degrees because they have been subtended by that same arc. So I said to you earlier that all of this, there are too many lines, so we need to focus on one circle. Begin with a circle that perhaps has got the most information. So I know that B1 is already on the circumference and it has 31 degrees. I went for CE because those positions were kind of begging me to kind of go to them and find out what was happening. But grade 11s, you can start at B1. You can say, let's go to B1 and let's see where B1 comes from. Can you see it comes from CE? And now go and find another angle that is subtended from CE. So that would give me that connection. So intersecting lines inside a circle will always give us that focal point to go and look for angles in the same segment. But find the angle, where does it come from? Find another angle that's subtended by that same line. So use your hands like a little maths dance. Okay, so that's 31. Now, earlier we said that this line was intersecting with that line. So if these lines intersect and they're straight, then this A4 and this A1 are vertically opposite angles. All of a sudden, the fact that you've now got this angle is 31, it's given me a cue, it's given me a clue for what to do next. So you need to start somewhere, and you always start with the given information. You always ask, I am given this, so that it's my starting point to be able to develop the relationships of the angles in the picture. So go back to it. We started with B1 as 31. We found that it comes from CE. CE also subtends A1, which is 31 degrees. Now, 31 degrees is sitting on the straight lines that I was given, so they are vertically opposite angles. Now we're going to do exactly the same thing. We're going to say A4 now is in the second circle. So A4 is coming from DF. Can you see how I'm using my fingers? DF. DF doesn't only subtend here. Where else does DF subtend? It subtends to B4. So B4 is also 31 degrees. So we started at B1 with 31. We found that it was equal to A1. We found that we had the vertically opposite angles. We then found in another circle that these were equal. At no stage have I actually been looking at where I'm going. I've just been working with what I'm given, and I've developed the various relationships. Now, if I want to try and find this whole angle, I can now say that in this triangle, all I'm missing is this angle D2. So my next question is, could I perhaps find D2? D2 is subtended by BF. BF subtends D2. What other angle does BF subtend? So I can subtend D2 on the circumference. I can also subtend at A3 on the circumference. So it's also equal to angle A3. Well, we can say that this DAC, can you see earlier we were told it's a double chord because it's a straight line. It's a straight line, so this angle is really 82 degrees, I think, because that's 31, that's 67, that adds up to 98, and 98 plus 82 will give me 180. So I needed D2. I was able to find it by using A3. I can now have that as A2, and then in that triangle there, it's obvious that that angle then is 67. So can you see how I've used the multiple theorems to be able to get to that? So now, how do we write that down? It's nice to do it as a puzzle on the diagram, but how do I write it down? Well, I would always start with where I began. So I began with B1 and A1. That's where I started. So always start with the angle that you don't know. So A1 is the one that I found, and it was the same as B1. The one that I'm finding, who's it connected to, and what is its value. So there must always be that link. You cannot just write A1 is equal to 31. Why is that? And the reason is because they're coming off the same chord, they are going to the same segment. So angles in same segment. You don't have to be fancy. A circle was given, so just angles in the same segment. Then we found A4, but A4 is also equal to A1, which we now found as 31 degrees. They are vertically opposite angles. And then we've got, let's go too far up, we had that B4 was equal to A4, and B4 was equal to A4, which was equal to 31 degrees. Again, we were using the angles in the same segment. And finally, we found A3, but A3 was equal to 82 degrees because we had a straight angle. And that gave us a clue into D2 as being the same as A3 because it was angles in the same segment. And ultimately, where we really wanted to get to was this angle there, which was really the sum of those two, so that one must be 67. So the angle we were looking for, therefore, F1 plus F2 was equal to 67. Angle sum. And then you've got to specify where you are. The marker's not going to guess where you've been in triangle DFB. Okay, I think Looney will send it over to you. We'll take a quick break.
Okay, cool. Before we take a break, Felicity is asking please explain how D2 is equal to F.
How D2 is equal to f.
Or should we take that after the break?
D2 is not equal to f. D2 is equal to A3.
Okay, cool.
Okay.
Okay.
All right. Super.
Felicity, I hope you got that. D2 is not equal to F, it's equal to A.
A3.
A3. I hope you got that. Mindset is we are going to take a very short break. I see you guys are answering the challenge question, the question on the page. So I hope we'll be choosing a winner soon. We will be. So stay glued, guys, and don't go anywhere. We are going to be back straight after this break. Welcome back, guys. If you've just joined us, our show is proudly brought to you by Macmillan, and Dina is in studio with us doing Euclidean Geometry. So Dina, straight back to you.
Thanks, Looney. Yes, let's get going. I've noticed that a lot of you, or we've noticed here in the studio, a lot of you are finding that angle D is 60. Sorry, try again. You've got to go back. It can't be 60. How can that be 60 if the equilateral triangle's over here? Come, come, come. Look for those isosceles. Look for the various sizes. D is not 60. Go back to the drawing board. While we carry on with cyclic quads. Right. A cyclic quadrilateral, what is it? A quadrilateral is said to be cyclic if all four of its vertices lie on the circumference of a circle. So all 4 points are on the circumference. So you have to take any 4 points and you draw in the various sides of that quadrilateral. We talk about that as being cyclic. 4 or more points, so points, when we specifically talk about the points, we say the points are concyclic, but the quad that is formed is cyclic. Cyclic quad, concyclic points. Right. And then we've got just a little explanation over here. If we take A, B, C, D, on the circumference, on the circumference, on the circumference, on the circumference, draw in the sides, that becomes a cyclic quad. And the properties that we have, the relationship between the opposite angles of a cyclic quad, is that if I take the sum of angle D and angle B1, if I add those two together, I'm going to get a very special value. I'm going to get 180 degrees. If I add this angle over here and this angle over there, angle C plus angle A is 180 degrees. So we have that the relationship between the opposite angles of the cyclic quad is a supplementary one. The sum of the opposite angles is supplementary. And you can actually prove that quite easily by using the angle at the center. So that for those of you who kind of don't believe that, you can just draw in your angle at the center. You'll talk about this angle being x, or talk about this angle being 2x. This angle is x. This angle over here is 360 minus 2x, which makes this angle over here 180 minus x. And so the sum of those two is 180. So you can prove that very easily with the angle at the center. Okay. Then there's another relationship that exists, and I'm just going to erase these little bits here so I can show you that we've said angle D and angle B1 add up to 180 degrees. So let's say that this angle here is x. Then this here, since it's a supplement, it must be 180 minus x. Okay? Now, if that is the case, when I produce AB, so if I produce AB to B2, which is what this is about, if AB is produced, then B2 is said to be an exterior angle. Okay? Then this angle over here, the supplement of that must be x. And now what we're saying is that this exterior angle to the cyclic quad is actually equal to the interior opposite angle. Okay. And so circle geometry uses two fundamental things. One, it's to use the theorem that the cyclic quad has these properties. But like you did in grade 10, where you were trying to prove that some of these shapes were actually parallelograms or kites or whatever it is, we've got exactly the same thing here. How are we going to prove that 4 points lie on the circumference? We would showcase, or we would show that the case where the opposite angles are supplementary would give us that 4 points to lie on the circle. So we talk about the converse, the opposite. If I give you a quadrilateral, and in this quadrilateral, I can show you that maybe this angle here is 120 degrees, and I can show you that this angle is 80 degrees, then this would not fit a circle because the sum of those angles is bigger than 180. But if I changed this slightly so that this angle over here is 60 degrees, then the sum of these two would be 180, and so these 4 points would be cyclic. So I can prove whether I've got a cyclic quadrilateral by proving that the opposite angles are supplementary, and also by using the fact that the exterior angle is equal to the interior opposite angle. So 2 properties. If I'm given a cyclic quad, I can tell you that those 2 things hold. But if I have opposite angle supplementary in a quad, or the exterior angle equals the interior opposite one, I can then conclude that the 4 points must lie on the circumference. Okay. And there's one last way of proving that a cyclic is quad. So let's just write these down. How do we prove that a quadrilateral is cyclic? Well, 1, prove 1 pair of opposite angles supplementary. Or, if I can't do that, can I prove that the exterior angle equals to the opposite interior angle? And don't get that confused with a triangle. Because remember, in the triangle, the exterior angle adds up to the 2 inside ones. Cyclic quad, it's 1-to-1 relationship. It's not equal to the sum. So we've got to be careful with that. And the third one, it's the converse of the angles in the same segment, is that if I have the converse of the butterfly theorem, so let's say I have a chord, and then this chord subtends an angle there of x degrees, and the same chord from the same 2 positions, I subtend another angle, and it's also x. Then I can say that position A, position B, position C, and position D must all lie on the circumference. So this is what we call prove that the angle subtended by a line segment subtend equal angles. If this is x and this is y, then that's not going to happen. So this is what we talk about when we say line segment, prove that the line segment DC subtends equal angles on the same side. And the same side is critical because if I subtend to B and then I had to subtend somewhere on the opposite side, then I wouldn't be able to prove that it's a cyclic quad. Okay, so those are the 3 ways of proving a cyclic quad. Okay, let's have a look at an example. All right, this question's very interesting. It comes from last year's supplementary exam from the grade 12 examination. And it really brings together quite a lot of ideas. And grade 11s, once you've worked with 1 or 2 ideas on one diagram, it's important that many lines sometimes are drawn, and we need to focus on those lines that are going to give us some information. So at the start, if I just look at this diagram, there's just lines everywhere, and we need to begin to focus on what's important. And it takes shape once you've been able to read the given. So I would encourage you, as a tip, always read the given once to just get a sense for where the lines are, or how many circles you've got, what kind of theorems are being asked. Then you read it again to make sure you've got all the information, because if you miss a diameter, or if you miss the center, tickets. You cannot go anywhere if you don't have any information. So it's important to read it a second time. And then when we get so carried away working on the diagram and finding things and so exciting and things are moving, just read it again to make sure that there isn't something lurking there that you've perhaps forgotten and you want to insert, which would actually be useful for some other questions. All right, so here we go. We've got O is the center, okay? Highlight that. O is the center. Without a center, we have no radii. Without a center, we have no diameters. So don't jump into the diagram and say, oh, there's a radius. Be careful. Did you start with a center? So we have a center, and we have a diameter. Got a diameter as well. Chord CF is produced. This is very important language. It's not just sitting there just so that they can waste your time reading. What does produced, what's the effect of produced? It means that we've got a straight line. And with straight lines, we've got straight angles. So we've got that meets chord BF, which has also been produced. Meets chord EB, produced at D. Okay. Chord EC is parallel to chord BF. Oftentimes on the diagram they'll have those, but that's just confirmation. So we've got some parallel lines. This is great. Got lots of information. And then we have also, they've given us one angle to work with, and this is fantastic. If they don't give you an angle to work with, then I would say you introduce some values. It's so much easier to work with geometry when I've got the angles. Okay, so I've got O1, and the most important thing that we read was that O was the center. So who goes from the center to the circumference? The radii, so I have that, would be equal to that, and also equal to this. So I've got 3 radii that are coming off that center. Most important, go to the center. I've got a center angle. It's subtended from CB. It's 2x. Who am I going to find? Angle at the center, I must have its partner at the circumference. Go and find the angle at the circumference. There we go. So angle E is half of that, so angle E must be x. Now, as I move to this new position on the circumference, I notice that this line, or the ray to angle x, is actually parallel. So obviously I'm going to look, who's the partner that's parallel to that? It's that line. Follow the transversal. That means that this angle is also x. Notice how I have not gone to any questions. I have just worked with the given information. You see how important it is. It's giving you all the clues, all the secrets to what's going on in that picture. So don't get all excited and go to the questions. First have a look at what the picture's given us. It's given us so much information. It's given us radii. It's given us an angle at the center, which we have a partner at the circumference. Now we're lying on the parallel line, so we've got some corresponding angles. This is wonderful. Anything else that we notice? Well, let's go and see what else we've got. In the diagram below, AB is a diameter. So AB is a diameter, which means that that's a straight line. So we can also find out what that angle there is if we wanted to. Okay. But we've just learned about cyclic quads. So let's go and see if we've got any of these cyclic quads. I've got E, I've got B, I've got F, and I've got C. So right there, with those 4 points, I've got a cyclic quad. What have we learned about cyclic quads? So let's color them in pink. So I've got C, I've got F, I've got B, I've got E. We've learned that the opposite angles exhibit a special property, that the opposite angles are supplementary. So this angle must be 180 minus x. Okay. Now, that CF we read, CF was produced. CF is produced, which means we have a straight line. If this was not a straight line, this angle here would not be x. That is very interesting, grade 11s, because what deductions do we make? We have 2 angles that are the same in a triangle. What's special about the triangle? Okay, this line is equal to that segment there, okay? Because it's isosceles. We've also got that there are another 4 points on the circumference. There's this one here, that one there, and that one there. So that's also a cyclic quad, which means that its opposite angles are also supplementary, so that angle is x as well. Or can you see how from E we could have subtended to A as well, and those are angles in the same segment, which simply means that we then have that this angle is also equal to x. Okay, now, the most common error that I see with grade 12 geometry when I mark is that they find any 4 points and they say that these angles must be supplementary. So those two must be supplementary. The cyclic quad, first go and find it. Go and color in the points and make sure that all 4 points are on the circumference. Because can you see, I'm going to add this angle and that one, and they don't add up to 180. So it means that this quad in here is not cyclic. The 4 points have to be on the circumference. Otherwise, we don't have a cyclic quad. So you need to really look at that. Okay, so if we now look at the questions, determine in terms of exercise of F1, where's F1? Well, we found it. There it is. Did we find that DF was equal to BD? There it is. Did we find that C1 is equal to C3? Well, we found that C1 plus C2 was equal to X. And the question is, could we say something about C2 and C3? Could we say something about that, that angle over there? And perhaps if we did a little bit of thinking, it would come from that original cyclic quad, remember that pink one, would be to say, well, I do know that if I produce, okay, I'm going to highlight it in green. So let's just highlight, okay, that doesn't work. Let's just undo that. Let's highlight it in yellow. So if we just outline the cyclic quad there, if we produce one of its sides, we create an exterior angle. And the exterior angle will be equal to the interior opposite angle. So that's also equal to X. So you've got C2 plus C3 is equal to X. And you've got C1 plus C2 is equal to X. The two totals are the same. Therefore, they've got a common angle. Therefore, C1 must be equal to C3. So just a little bit of thinking around there. But lots of cyclic quads and lots of working with the properties of the cyclic quads. I think it's time for a short break.
Okay. Mindset is we are going to take a very short break. My head is spinning just from watching Dina work out all of these things. So I hope you guys are fine at home. So let's take a break, go drink some water, get some juice, get your brain fluid flowing again, you know. So we'll be back straight after this. Welcome back, Mindsetters. I hope your brain fluid is flowing again and you guys are calmed down and you're fine. I hope the challenge question is not tricking you too much. But Dina will give you a few tips because you want those three of you to win one of those books, guys. All three of those books must go away on today's show. So, Dina, please help the Mindsetters.
Okay, I've got the power. I've got the answer. Grade 11s? Very, very simple. Maybe there's some grade 10s also trying the challenge, and really grade 10s this is also for you. You can do this one as well. Grade 9s, even you can try as well. Right, the real secret is to let the angle that you don't know, let that be X, and try and work with the properties of the triangle. It really, really is that simple. So if you look on your diagram, if you let that angle there be X, then I'm sure within the next 5 minutes, you'll have that answer for us. Remember, we want you to get it right. It's Science Week. We want to celebrate you being geniuses. So let's work on that angle being X, see what you can do with that, and post your answers. We want to give out those books. Right, and then back to grade 11. This the grade 9s can't do at this stage. It's not part of their syllabus just yet, but we have been talking this afternoon about what makes a quadrilateral cyclic, the fact that all 4 points are on the circumference. We've talked about how to prove that a quadrilateral is cyclic. And in the last section, I showed you how to use the properties of the quad. We're now going to reverse it. A very popular question in circular geometry is to prove that a quadrilateral is actually cyclic. And the first thing that you must do is you must actually outline the shape. Because remember, if you're trying to prove that it's cyclic, you're not going to give a circumference. You're not going to be given a circle. So you're kind of working in a vacuum. So it's very important to just take a highlighter and outline your shape. Okay, so let's get to it. Two circles intersect at B and A. CBD is a double chord. CSE and DTE are drawn to meet BA produced in E, and SA and AT are drawn. So all that information there is just a position for us where each of the points are, where each of the lines are, and it's not given us anything interesting. There's no center, there's no diameter, there's nothing to work with. There's just lines, okay? Then they've also given us that B1 is X and A4 is equal to Y, and we need to prove that this shape is actually a cyclic quad. So let us go to the shape. Everybody take your colored pen. We're all going to do this together. SATE, and we're going to outline that shape. So SATE. Okay. And we've got, as I said, CBD is a double chord. Why are they giving us that information? Because CB is a straight line. CB is a chord in the circle. BD is a chord in that circle. They're not congruent circles. They haven't talked about that, so we can't assume that. But they've given us that B1 and A4 is equal to Y. And we've got no other information. If we go back to it and we just read it again, they intersect. We've got a double chord. We've got those lines that are drawn to meet BA produced. So BA is produced. BA is produced, which means that that's 180 minus Y. Okay. And now we want to prove that that blue shape, it can be cyclic. Meaning we want to prove that ASET, those 4 points could lie on the circumference of the circle. What did we do just a few minutes ago? We found 3 ways of proving it's cyclic. Either its opposite angles must add up to 180, or its exterior angle must equal to its interior angle, or the diagonals must subtend equal angles. Well, there have been no diagonals drawn, so I'm not going to go that route. But if I took ES as being produced to C, then can you see that S1 is the exterior angle, and the interior angle has got to be opposite it. So this would be adjacent to it. This would be on the same line. Opposite means it's got to be directly the opposite vertex. So the 2 vertices have got to be opposite each other. So if you put your fingers on there, you'll see that they're opposite. These are not opposite. They are adjacent. These points are on the same line. So make sure that, okay, that's an option for us. We can work with that if we wanted to. And then if we go to what's given, okay, so that's where we're going. If we look at what's been given, we go C, B, A, S. Ah, what is that? Those points on the circumference. C, B, A, S on the circumference. So what kind of shape is that? There are on the circle. So C, B, A, S is a cyclic quad. If it is cyclic, then what do we know? That its opposite angles are supplementary. So that gives me that that angle is 180 minus X. Okay? And we've also got that this line is straight. So how much is this angle over here? That's also X. Okay? And we're going to write down as many angles as we possibly can. We're also given that this is a double chord, so if this one's X, how big is B2? 180 minus X. Okay, now, I was in CBAS as my cyclic quad. I've now moved into this angle here, which is in another circle. So let's see if we can find some cyclic quads there, because this geometry is all about cyclic quads. So there's a point, there's a point, there's a point, there's a point. So this one's also cyclic. And if that is cyclic, then this angle over here is equal to X. And this angle over here, it must be 180 minus X. So it really didn't matter which route we took. We could have shown that the exterior there is equal to the interior opposite, which it is, or we could have shown that the pair is opposite, is supplementary, or we could have shown that that angle is equal to that angle. So there's actually 3 different ways of actually finding that is cyclic. Okay, so now if we had to just write it up, where did we start? Okay, we started off with either that as being supplementary because we needed to get to T1, or we could have said we could have started with this angle over here. So if you want to go with B1 and S1, you would write S1 is equal to 180 minus B1, the relationship. And the reason that we use is opposite angles in cyclic quad. But because there were two there, you need to mention which one. So be specific, CBAS. Okay? And that would mean, therefore, that S1 is 180 minus x. If we had then said that B2 was 180 minus x because of the straight angle, then we can automatically say that T1 is 180 minus B2 because opposite angles in cyclic quad, and in this case we have BDAT, and therefore T1 is equal to 108 is equal to x. And looking at T1 and S2, we can then say for S2 is equal to x, these would be the same, and therefore that blue shape is a cyclic quad. And I'll leave you to work on why is STDC a cyclic quadrilateral. Okay. All right, folks, over to Luni.
Okay. Mindsetters, thank you so much for joining us and for tuning in. We will announce the winner of those 3 books probably in the next show. So hope you stay glued to your screens. Thank you so much for doing maths with Dina and I. We will see you next time. Thank you to Macmillan for sponsoring our show and for giving us a great show. Until next time, guys. Bye.